The good thing about not starting on time is that you have to prepare less slides. So that's yeah, I'm Carsten. And the original title was multi-part zero knowledge proofs from symmetric key primitives, but then we narrowed it down to just talking about MPC in the head because that's all we know about. When it comes to building zero knowledge proofs, at least Peter and me, like Peter is different. So the plan for the day, Akira already hinted at that. Thanks for the introduction, Akira. Is that we're gonna have 3 parts. First lecture, which is now, which is going to be the basics of this thing called MPC in the head. What is that? Then a bit more about, like, I guess, signatures, and if we have time, talking about the so-called Ligero proof system. And something called a vole. The English speakers here might be wondering what little rats are going to have to do with zero knowledge proofs, but you'll be surprised what they do. And then there's also going to be something called vole in the heads. We're not going to put these rats into people's heads. Something else is going to happen. And something called feast, that also feast, whatever, that Kira also hinted at, which is a digital signature scheme that is quite performant and nice. So yeah, so much about this. And why MPC in the head? Well, like both Peter and me originally come from a field called multi-party computation, and like this is our way of working on zero knowledge without actually leaving the field of multi-party computation. So we can apply for grants from funders saying, like, we do this fancy thing called zero knowledge that you can use for blockchains and everything, while at the same time still doing MPC. So that is great. So now is session 1 out of 3. Well, what is this session going to be about? Well, first there's this thing called multi-party computation. What is this? Then we're going to go from there to putting that into the head of someone. And finally talking about the so-called KKW construction, which is one way of building MPC in the head, probably the easiest way of building these zero knowledge proof systems. Okay. So you saw zero knowledge proofs yesterday, and you saw like the standard definition, which talks about indistinguishability and like how to get like these 3 different properties: completeness, soundness, or knowledge soundness, which was talked about yesterday, the more interesting one, and then of course the zero knowledge property. But I want to talk about, or I want to say that you can introduce or formalize this also in a different way. Right? Instead of giving separate definitions for all these things, you can take an approach from the more modern approach of cryptography, which is instead of giving different definitions, we formalize this as kind of one building block, which is called an ideal functionality. So an ideal functionality is some kind of blob that our prover and our verifier, or Alice and Bob, or however you want to call them, have access to. Like some kind of magic box. It's like a trustworthy magic box. Okay, so both Alice and Bob know, like, this magic box is going to do for them what they want it to. It's going to behave as it's supposed to behave. Some kind of a trusted third party. Okay, and this magic box, this is, yeah, cryptographers usually call them ideal functionalities. This is going to do one thing and one thing only, right? So it first waits for input from Alice and Bob, and Alice is going to input some kind of circuit describing a computation, and then a witness. Okay, and she inputs that into the box. Nothing else happens. And then Bob says, yeah, well, that computation looks kind of cool, so I'll, like, you know, let's do that computation on that witness there, right? That I have no idea about. And then the magic box is going to say, well, I'll evaluate the circuit on this witness, and if it outputs 1, I'll output 1, otherwise I'll output 0. And then I give that output to Bob. And so Alice has the guarantee that this is what the Bob is, not the Bob, the functionality, going to output to the Bob, not the Bob to the functionality. And Bob knows, you know, that you know, that's all Alice gets there. So having this box already gives you everything you want for a zero knowledge proof, right? Well, it is complete, right? If C on W equals 1, Bob learns 1, otherwise he learns 0, right? So we get completeness. Everybody follows the protocol. Magic box is going to give you what you want. Well, unless Alice inputs a, no, let's first do zero knowledge, right? So what does Bob learn in this case, right? So from the box itself being so nicey and boxy, the only thing that the verifier ever sees is this output bit, which coincides to this evaluation here. So this is zero knowledge because the only thing the verifier learns is this bit of information: is the proof valid or not? It's the exact same thing that he or she also learned in the classic definition of zero knowledge. And it's knowledge sound because we also have security against the cheating prover, right? Because unless the prover inputs a witness that satisfies the circuit, the box is not going to output one to the verifier, right? So this box guarantees security against the cheating verifier and the cheating prover, right? So it gives us completeness, zero knowledge, and also knowledge soundness because Alice intuitively has to input this witness into the box, so she has to know a witness. Okay? That's an alternative way of phrasing it, where instead of having different definitions, we just assume the existence of a nice box that does things for us. And now that we're talking about boxes in cryptography, let me introduce you to a different box. That's called the multi-party computation box. Because like once we abstract a functionality to do something for us, right? Why not replace this functionality by a different functionality and ask, well, maybe we can realize this using interactive protocols too. And the different box is called multi-party computation. Well, what is this? Well, it's a box that does the following. Everybody also kind of agrees on the computation that you want to do. And in addition, everybody has a secret input. And now, instead of only like computing on Alice's input, now there are more parties and the functionality is going to compute on everybody's input, evaluating the circuit, computing some outputs, and afterwards, after it's done, giving the outputs to everybody. Or maybe just bots, right? But that's the guarantee you get. So far, so good. Multi-party computation is abstracting it, is just doing that, right? So we're having access to a trusted third party, and that third party like takes a secret input from everyone, and it correctly evaluates the circuit on it, computes the outputs, and gives the outputs to everybody. Like everybody's getting the outputs supposed to get. Yes?
What happens if they have different circuits C passed into it?
I mean, if, for example, if the parties don't really agree on the computation they want to do, then just no computation is going to happen. So you'd have to formalize these corner cases. I left that out for simplicity because otherwise, like, we're going to get into trouble. We're going to be in a scenario where parties always agree on the computation they want to do. But thanks, good question. So we get correctness, like everybody gets the output they're supposed to get. And we also get privacy, right? Because everybody just learns whatever the functionality reveals to them and nothing else, right? If that circuit, of course, reveals everybody else's input to you, then multi-party computation doesn't guarantee anything. Because the computation leaks this information. But otherwise, you only learn like whatever you're supposed to learn from evaluating the circuit and what you have like as your own input, but you're not learning anything else, right? Why, like, party one doesn't learn Y2 unless inherently by, the computation of the circuit, there's a correlation between these outputs. Does that make sense? Okay, it's just a different box. Right? It's a different box, it's a different ideal functionality. And since we're all cryptographers and we're not just, assuming, boxes and ideal things and then just get on with our lives, but we actually want to realize these things and use them in practice. So what is a multi-party computation scheme? And before like saying that you can, of course, build these things, right? I should mention that, well, this is nicely a restricted form of zero knowledge is a restricted form of this, right? Multi-party computation has potentially many parties, but if you only take two of them, and if the second party doesn't have any input, then this just becomes zero knowledge. Right? So multi-party computation is a generalization of what zero knowledge is. Is that clear? Or have I already lost everybody like 10 minutes into the... I didn't. Good. But so what is multi-party computation then? Not assuming a box, right? So the boxes are like, okay, we all know that like paper cardboard boxes exist, right? But these magic boxes don't exist. But in practice, like multi-party computation exists. What is it? Well, multi-party computation is an interactive protocol between different parties that realizes such an ideal. And it would be boring unless some people could potentially be malicious, right? So we assume that some of the parties participating in the multi-party computation protocol are potentially misbehaving or leaking information, revealing information. So we assume that there's what is called an adversary, and that adversary corrupts some of the parties, right? In this example, party 2 and party 5, these are going to be these like computers here with the little devil's horns, right? These are kind of like controlled by some malicious, nefarious identity we call the adversary. Okay. The multi-party computation protocol is happening in the presence of such an adversary. Right? And what we want from it, like going back to this ideal functionality definition, is of course correctness, right? If parties learn the output, then it's the right output they're supposed to learn. It's like dishonest parties can't make you learn anything but the right output, or you learn that, you know, something went wrong. But at least, like, if you get something, you get the guarantee that it's the right thing. And then there are two properties which are dependent on how dishonest parties behave. Right? Yesterday we saw this, like, right? Yesterday, John talked about there being honest verifier zero knowledge and, like, you know, the real zero knowledge, right? So in honest verifier zero knowledge, you know that the person on the other side is going to give you, like, it's going to behave according to the protocol, but might want to learn a bit extra. Whereas, like, real zero knowledge, right, there you don't know what the verifier is going to do, right? You don't know what kind of strategies it follows. In multi-party computation, you do this, you distinguish also these two cases. You might have, you might be in a situation where you assume that your attacker kind of follows the protocol but wants to learn something extra, right? So your attacker controls parties 2 and 5, but he lets them do what they're supposed to do. But, like, from, like, looking at the messages that they get, he wants to learn something extra about, you know, maybe somebody else's secret input, like party 1's secret inputs, right? So maybe that's what the adversary is after. But he's gonna behave as if he's, like, part of the protocol now. And this is what we call the property that we call privacy, which means, like, if you have T privacy, that means that if the attacker corrupts up to T parties, it can't learn anything beyond the outputs that these parties get from the multi-party computation and the inputs that they have, right? So in this case, if this protocol is secure against 2 corruptions, bless you, what this means is that the adversary will, of course, learn the input of the corruption part, but it's going to learn the input W2 and it's going to learn the input W5. And the adversary is also going to learn the output of party 2 and the output of party 5. But except for that, if the protocol is secure, has 2 privacy, this is the only information the attacker is going to learn. All the rest can be simulated, like, according to a similar definition as we saw yesterday. That make sense?
But yeah, they don't have to behave according to the protocol.
I mean, for privacy, we assume, like, let's assume that, like, what you usually call semi-honest behavior, right? As I said, right, here we assume that the parties follow the protocol, and then you have security, like, if they follow the protocol, against them, like, trying to learn something extra while they follow the protocol. You can, of course, have, and I guess that's what you wanted to hint at, have a stronger property, which would be robustness, which is, like, somewhat related. I'll just, like, for here, I want to combine them all in different ways, but like, another guarantee that you might want to have is that if you corrupt some parties, you cannot break this correctness guarantee, right? So you cannot, if I corrupt 2 parties, I cannot make the honest parties get an incorrect output. This is what I would introduce here as robustness, right? And so an MPC protocol can also have, in this case, for example, 2 robustness, which is, now if the parties misbehave in whichever way they want, they may not be able to make the honest parties output something else but what they want, well, we're supposed to get, or the honest parties learn that, you know, something went wrong in the multi-party computation. I just want to, like, distinguish these 2 cases. You can, of course, have an MPC protocol that has the same privacy and robustness level. Like, usually if you do build something from, like, for the expert from Shamir sharing, right, you would have the same privacy and robustness level. Yes.
I'm just confused about the, like, semi-honest and active clauses in this definition. So you assume semi-active and privacy. Semi-honest, sorry. So you assume semi-honest. And
This is kind of a guarantee I get against the this obviously makes sense in a semi-honest setting. I can also extend this, of course, to the fully malicious setting.
yeah, does it apply
This is-
to the fully malicious setting or not?
I mean,
Do you call generalize your knowledge with the active adversaries as privacy as well, or is it just a different?
I mean, you usually also have, of course, privacy. Here, I just want to because if once we go to MPC in the head, like this kind of doesn't really make sense anymore, because there the adversary is always kind of the prover, and that's why right, information leakage doesn't really make sense for a like to consider for a prover that is misbehaving. Like, you're just giving away information to the verifier. Who cares? That's like not my problem. That's why I separate them here. But usually, if you look at MPC in general, you also want privacy against misbehaving parties, depending on the MPC scheme you're building. What purpose for? But yeah, good question. Might not have been the best.
If I read privacy now somewhere in a paper, does it usually refer to like fully malicious?
I mean, usually
or
usually it does, but so for what we are going to look at, which is MPC in the head, not like there we don't care.
okay, I get it.
There we don't care, because misbehaving parties in a multi-party computation only leak information to the verifier, and we don't care about that. Like, if I am a dishonest prover and I leak information to the verifier, well, you shot yourself in the foot. I don't care. I really don't care. But general MPC, yes, of course you want the, depending on your adversarial. And now I said that parties can be corrupted, right? There's an adversary that can corrupt parties, and there are two ways of doing that. One is, and then these like, if you want to write a security proof, you have to take like these cases into consideration. So one is called the static model. So, and the other one then the adaptive. So the static model of a security proof is kind of similar to what we saw yesterday, right? You know that either the prover or either the verifier is corrupted, but you know it from the outset. And the same in a multi-party computation setting. You in a static, if you consider a static security setting, you kind of know in advance who the adversary is going to corrupt. Like, when you start your multi-party computation session, somehow the adversary is going to tell you, well, I'm going to misbehave, but it's going to be parties 2 and 5. It's kind of a strong assumption to make, right? But it makes designing MPC protocols easier. The other way of doing it is the more realistic one, which is called adaptive security. There you start your multi-party computation, right? And then at some point, the adversary is going to come around and be like, well, I feel like party 2 today. And then the adversary lets the MPC protocol run a little bit more. And then he's like, well, party 5 is now also corrupted. Of course, this is like, intuitively, this generalizes static security. You actually need to prove that adaptive security implies static security. It's not always easily following, but in some cases it does. In most cases it does. But yeah, right. So this is now you're in a setting where the adversary can come at any point of time. Yes.
How about mobile?
We don't care about mobile adversaries for MPC in the head.
Why?
Because you're kind of never uncorrupting parties. You're never showing, let's say, the messages from round 2 from party 2, and then the messages from party 3 in the other rounds or so. It doesn't really give you anything when you design protocol. Well, it might. Nobody has ever looked into this. Well, I would doubt that you can give that you can build an efficient zero-knowledge proof system in this case. Yes.
You said that adaptive security does not necessarily imply static, but can't we just always in adaptive setting corrupt from the beginning a fixed subset? And then it is the same.
Like there are some technicalities for why these things don't always go through. Okay.
Maybe it's too subtle to just explain. And
Yeah, there are. I think there are some border cases where things go haywire. So, as with everything, in cryptography. But you can generally think about adaptive security as a generalization of static security. Yes.
Stupid foundational question. I've never seen any definition that kind of doesn't assume that adversary explicitly states who is corrupted.
I mean, the adversary states it explicitly, but not in the beginning.
Yeah, but like there's no definition. We cannot work with definitions where adversary does not explicitly state who is corrupted. We cannot like assume. We cannot make guesses on corruption. Or
No, not really.
is there a definition like that?
So that won't work. And the point is because of how you then actually define security. We're going to get to that in a bit. Because you do this using the simulation paradigm.
Yes.
And if you want to simulate some parties, right, you need to know who is corrupt and who are the honest people that you are going to simulate like behavior of, right? If you don't have that, like there's nothing how you can build a security proof.
Just one comment on that. So if we don't, so for the security proof, of course, we can maybe know who is corrupted, but it doesn't mean that in practice, if you use the system, the security, we have to know.
Yeah, the MPC, like, that is of course correct, right? So the multi-party computation scheme doesn't care. Like, otherwise, we have a very simple way of doing MPC, right? If you know at the outset of the MPC that party 2 is always corrupted, you just send all information to party 1, let it do the computation in plain, and output the outputs to everybody else. It's a very simple MPC scheme. So protocols that are secure, if you know who is the adversary, are rather easy to build. So they are a bit boring. Yes.
Just to confirm if I understood correctly, so you can be like you can corrupt a party, and in the next iteration or something, you cannot make it honest again and do it.
Yes, I mean, you are correct. Like in the models I'm talking about here, you can't do that. What Elena was mentioning earlier, so-called mobile adversaries, they can do that. But for MPC-in-the-head, we usually don't care about mobile adversaries. Because like building secure protocols against them is very hard. But I don't see how to exploit them to build more efficient protocols. Anyway, yesterday we talked about the view of a prover or the view of the verifier, right? Which are the messages and like the randomness of the party when you start. And you can make a similar definition of a view of a party in multi-party computation, right? So view of a party is, for example, the view of party 1 is right, the input of party 1, the output of party 1, and like all the messages it ever sends and receives. Okay, we just call this thing a view. And then of course, if you're an adversary, then you know all the parties that you corrupt are like the views that you know are just like all the views from all the parties you have corrupted. Like having this, we can now make a very similar like security definition that as we did yesterday, based on this so-called simulation paradigm, right? So we're gonna set this up as like 2 worlds as a security experiment. Yesterday, by this indistinguishability argument assumes that there are 2 worlds. For example, for zero knowledge, right? One world where you have the witness as the prover, and the other world where you're simulating everything without having the witness. And here we argue security as a similar simulation experiment, right? So on one hand, we have the real world, whatever that means, right? So there are parties, there are honest parties, dishonest parties, they run an MPC protocol, and in the end they get outputs, and that's what happens. And then there's the ideal world where our adversary has corrupted, for example, these 2 fellows here. But instead of having honest parties being like physically there and being actual computers, right, like these here, instead these parties are simulated by some kind of simulator. Right? As in the zero knowledge proof, as like the definition of a zero knowledge proof yesterday, where we simulated the prover, now we're simulating kind of the other parties that are there. Right? It's done by an entity called the simulator. And this entity, what does it do? Well, it talks to the dishonest parties, kind of talks to the adversary, but the adversary controls the dishonest party, so it kind of talks to the dishonest parties. And generates the messages that like honest parties would send to the dishonest parties, right? So it generates those, and it gets the messages from the dishonest parties and processes them. But now we're not just getting like 1 bit of information, right? If something is true or false, right? Now instead we get kind of the output of this computation, right? So our simulator now talks to this ideal functionality. It kind of has to figure out what are the inputs that these parties here are having. It then gets the outputs that these parties are going to get, and it simulates a multi-party computation protocol, oopsies, such that the dishonest parties in the end think, these are the outputs I'm supposed to get, right? They're satisfied. And what we want to have is that both of these worlds are indistinguishable, which is similar to the case that we had yesterday for the zero knowledge, like arguing zero knowledge, right? Yeah, you have two worlds, an ideal and the real world, and both of them are indistinguishable. This is the same thing, just generalized to the definition of multi-party computation instead of just the zero knowledge proof. And it encompasses both soundness property. If you think like if you look at it from this perspective, both the soundness and the zero knowledge property, because you're not just simulating the messages that these parties are getting, right? You also have to kind of feed the ideal functionality, the inputs of the dishonest parties. So this simulator also has to figure out these parties' inputs. So in this like this it also has to behave like an extractor in the zero knowledge definition. If you ever care about these kind of things, universally composable security definitions, this kind of stuff, then you get there. I just wanted to show you this as like an alternative way of formalizing security. That's too much. Well, not gonna do this. So let's get into let's set up things for MPC in the head, and for this we're going to need two more flavors of multi-party computation, and one is called client-server MPC, and it does what you think it does. It's like a very simple setting where instead of using all like initially we said like every party has an input, every party gets an output. In practice, you might not want to do that, right? In practice, there might be like two people, party one and party two, and they are the only ones who have inputs. Now they are going to send some information to the remaining three servers. Like these are the clients, these are the servers, and after that, that's like boop, go away, and not going to say anything anymore. Now these three servers are going to do some kind of computation among each other. And afterwards, they're going to send some messages to clients, and the clients learn their outputs. But in the process, these three servers never got any information about the inputs that the two clients had, nor did they learn the outputs. Only these two parties here did. This is what is called client-server MPC. There are some parties that act as clients. They only feed some information to the servers and get some messages from the servers afterwards. And then there are the parties who are doing the actual computation, and those we call the servers. Okay. I mean, the same way how your phone talks to Google and gets a result from Google. And then there's something in MPC which we call the pre-processing model, and that's a very interesting one. And in the pre-processing model, you're kind of I said that, you know, like we can define MPC and what it does and why it's secure using, you know, some idealized functionality that does things for you. And MPC in the pre-processing model is somewhat similar. It's like you're running an MPC protocol, but you're assuming some kind of external help. But what is the external help going to do? Well, the external help is some idealized party over here. Like it is honest, which is very clear from this there. And what this party does is before the whole multi-party computation, it's going to take an efficiently sampled distribution D. It's going to sample, let's say, it's going to sample something from this distribution, and then everybody is going to get their share from this distribution, right? So this distribution might be 5 correlated variables, and I'm just going to give everybody whatever I sampled. And then the ideal party is going away, and only afterwards the parties get their inputs and then run the computation based on these inputs. Yes.
Is that more like universal reference string or like structured reference string?
All these things you can assume are some kind of idealized model.
Okay, so this can be quite strong.
Yes. This can be like MPC in the preprocessing. Like if you think about this, yes, this abstracts away something like a common reference string in or you know, common reference string, common random string, all these kind of things. But it can be more powerful than that, right? You can, for example, also give parties something, some values that are correlated but not identical. And we're going to use that later to build zero knowledge proofs. Like this party over here on the right side, like this is trusted, right? This is going to sample something from this distribution, giving everybody some part of it. But R5 and R4 might be correlated in some way, but might not be the same. If they are the same, you have something like a common random string. But yeah, good question. Okay, so the party, this trusted, yes.
Sorry, so is this, would you write a different ideal functionality for something that does this kind of like ideal party, or would this still be an implementation of the original ideal functionality we saw?
No, I mean, this is it's just like a generalization of MPC. You would then potentially realize this functionality again using a multi-party computation protocol. But if we want to build zero knowledge proofs, there's actually a much easier way of realizing this functionality. You just say the prover is that functionality. And that simplifies our lives. If you're doing MPC, like now some people are like, what is he talking about? So if you're doing MPC, usually like realizing this thing is a hassle if you're like building actual MPC. But if you're in a zero knowledge setting, there might be an easier way of realizing this functionality. Because all these parties here are controlled by the prover, then this thing can also be controlled by the prover, and life gets a little bit easier. We are going to get there in a bit. Yes.
Do parties have to keep the R secret?
Yes. Of course, if the adversary corrupts them, the adversary can see the share from the correlated randomness. Right? But they don't just publicly announce this is my correlated randomness. Otherwise, we didn't get much here. Okay. Anyways, parties get that. Then they get the inputs. So the input is not correlated to the correlated randomness that the parties got. And then they run their MPC. And the cool thing is that you can build MPC protocols that are much faster, assuming this nice thing here on the right side. So we're going to exploit that. Or not us, but people who build MPC-in-the-head protocols. Then MPC outputs, yada yada. So yeah, examples for this kind of correlated randomness. This can be all kinds of stuff. This can be just random bits. It's helpful for whatever you're building there. It can be like random other correlated stuff. It can be shares of a secret key, if this is necessary for a protocol that you build. Like there are all kinds. Like this can be anything that you share there. John introduced commitments yesterday, right? So I'll not do the commitment slide. I have one thing more, which is secret sharing. Who of you has heard about secret sharing? Peter doesn't count. Who has not heard about secret sharing? Okay, I'll skip that too. Good. Then we can now build MPC in the head. We have everything. Also, we have like 9 minutes left before you all want to have some coffee. So let's better like hurry up and build the MPC in the head. So how does it work? It's like a great idea that Ishai and others had in like probably before 2008, but then the paper got published, and works as follows. So you have your prover, the prover has a witness, and you have the verifier on the right side. Okay. And now instead of like directly talking to each other, we're going to use MPC, and to the surprise of everybody, we're going to run it in the head of somebody. And the person who is going to run it in the head is like this guy here, our prover. So our prover imagines, he makes up in its head a multi-party computation protocol, and it runs the parties kind of in its head. It's like spinning up a lot of virtual machines, Docker containers, and let's each of these containers simulate one party in the multi-party computation scheme, and then let them talk to each other. Okay. Like so far so good. Like it's just a kind of a mental experiment that the prover does. And what does it do? Well, it takes its witness and it secret shares the witness to all of these parties. Okay. So far everybody's following. And now what can these parties do? Well, these parties can now check, since they can do any kind of computation, what can they do? They in particular can run the circuit that verifies the witness on the secret shared witness. So just reconstruct the witness in MPC, and then they evaluate the circuit, and then they let the it lets these parties output the outputs of the multi-party computation to the verifier. That's what MPC in the head does. Now you might say, well, can't these parties lie? Right? Everything happens so far in the head of the prover. So there's some additional tweak that we need, which is the prover is going to commit to what all of these parties are doing, the views of all of these parties, to their inputs and their outputs and all the communication that they've sent to each other. Okay, it's going to send the commitments over to the verifier. The verifier only sees the commitments; he doesn't know yet what is going on in there. And then the verifier is going to say, "Well, open me a subset of these, T of them." Okay. And the prover does that. And what does the verifier do? Well, it checks, did all of these parties behave honestly in the multi-party computation protocol? And like, are the outputs that they're getting actually saying that the circuit was evaluated correctly? And then you actually know, right? If the parties themselves say, well, the MPC protocol ran correctly, and if they say, well, the output that I got says that the witness was valid, then as a verifier, I have a guarantee that the witness that was secret shared here was actually the right thing. Now, all we need to show is that this thing is correct, sound, and zero knowledge. Yes.
What's T? How does it relate to the assumptions on the MPC?
We'll get there in a moment. Like it opens some set of parties. Now we have to choose T in a smart way, so that it's zero knowledge, but it's also sound. So let's do that before you all get your coffee. Like this time I know that there's coffee out there and not beer. Like I'm not over promising, I hope. you can actually view this as some, and I introduced this client server model earlier, because you can view this as some instead of putting the parties in the head of the prover, you can look at MPC in the head as a client server multi-party computation, where the prover and the verifier are each one client. Like the prover is one client, the verifier is the other client. And initially, this client called the prover is just going to secret share its input, the witness, to all of the parties doing the computation. Then the parties do the computation. And afterwards, they open the output to the verifier, this other party. So it's some kind of client server MPC. Right? That's how we can abstract this as well. Mad PowerPoint skills. And this is going to help us later on when we talk about other MPC in the head schemes like Ligero, because they can be neatly abstracted in this way. I don't think it's going to help us because we're not going to get there because I'm talking too much, but let's argue security and then cookies. So why is this thing complete? Well, we said, like, ignore the for add, right? That is a typo. But we said that we assume that the circuit evaluates to 1 if like the prover actually has a witness, right? And that witness is valid for some relation. Then the MPC protocol evaluates the circuit, and all of the parties are actually terminating with something that says, yay, it's the correct output, right? They all get the output 1. That's the guarantee from the correctness of the multi-party computation scheme. So that's why this protocol is complete. So if the prover and the verifier are honest, everything works according to plan. That is a good sanity check. Good. Everybody can follow so far? Nice. So now comes soundness. And the trick about the soundness is that the prover has to decide which parties will cheat before it knows which parties the verifier is going to look at. And this is what we're going to use in order to prove soundness or even knowledge soundness of this protocol. Right? Because the prover runs the MPC in its head, commits to the views, sends off the views, and only then the verifier decides which views to look at. Okay. So, and yeah, the prover checks, like, do the views of the parties make sense with each other, right? And that's how we are going to figure out if somebody has been cheating. And of course, so we assume an MPC protocol that has some robustness against cheating parties, right? So let's say a protocol is robust against, let's say 2 cheating parties, right? Or 1 cheating party. Right? One party can always like deviate from the protocol, and if it does, then 2 things can happen. everybody else, like all the honest parties, either like get the right output of the computation, or they say everything failed. So everything failed is not something that the prover wants the verifier to see, right? So if it's robust against one cheating party, then like we don't have to do anything if you know, if the prover is guaranteed to only corrupt one party. But that means if we have this robustness, let's say one robustness, right? The prover must always corrupt more than one party in order to cheat, right? It must make more than one party in the MPC protocol deviate from the protocol. Otherwise, like the protocol is going to be honest to the verifier, and the prover doesn't want that to be seen by the verifier. And now we can just do some kind of simple counting argument to argue like what's the probability of the verifier catching such a cheating prover. Okay. So okay, here the example is a protocol that is, let's say, private against 2 corruptions, and also secure against that's 2 corruption, like 2 parties misbehaving in the protocol. So what does it mean? So if the adversary corrupts 2 parties, then the protocol gives the correct output to the verifier. That shouldn't happen. So the adversary has to corrupt 3 parties if it wants to cheat. If I'm a dishonest prover, I don't have a witness, I need 3 parties in this protocol to cheat. Okay. And we make another simplifying assumption, which is that the communication is just everybody sends the same thing to everyone. That's also what is going to happen in this KKW protocol later. Like the security argument gets a bit more complicated if this is not the communication behavior, but we make this assumption, okay? So there are 3 parties that are misbehaving. They are not following the protocol. Okay, and the other 2, they have been following the protocol. So now what's my chance as a verifier to figure out that something went wrong? And we're going to use this, we're going to let the verifier here pick 2 parties, okay? It's going to look, so it's going to get the commitments of everybody, and then it's going to pick 2 parties, this one and this one. If the verifier picked both of the honest parties, well, he's out of luck, right? These parties have been following the protocol honestly, he can't detect any cheating. If it's been 2 of the dishonest parties, the verifier is also out of luck, because, you know, these are like misbehaving parties, but like they might have been misbehaving in a way that only is visible for the honest parties, right? But with each other, maybe I can make things be consistent still in a way, right? I can't use this party to detect that this party has been cheating. But if I have an honest and a dishonest party, then the prover is out of luck. Why is that? Well, what is cheating, right? Cheating either means this guy here sent the wrong share here. I see that. Or this party has sent the wrong message to everybody else. But I assume broadcast communication. So this one here sees that this one here has a different message received than this one was supposed to send. So I see that something went wrong in the MPC protocol and I detect cheating. Now I just need to count the cases, right? There are 4 subsets where, as a verifier, I either get only honest or only dishonest parties. And then there are 6 subsets where I get 1 honest and 1 dishonest party. So my chance of detecting that there was cheating is more than 50%. Now I can just do parallel repetition of this thing, like run a multiple of these things in parallel to get security guarantee as, like soundness guarantee as nice as I want to want. Yes?
Is this like cut and choose style?
Yes. Okay. It's like some cut and choose combinatorial argument that people use all the time. So here I of course use that, you know, if this person here announces, or this server announces something wrong, then this party can always detect it. That might not always be the case in all MPC protocols, but you can make a different kind of analysis and that still works if you don't make this broadcast assumption. Yes, there were 2 questions.
And what happens if all the parties are dishonest? Like which property did you use?
So if all the parties are dishonest, so either they send something weird to each other. I think then you're in a situation where like you still see that something went off. Like either like no like correct message was sent to the verifier, but you cannot make like the parties like views consistent, like if the views are consistent with each other, and I don't detect that something was weird, like going on, then you followed the protocol, so you kind of were an honest party to begin with, like even if it was corrupted by the adversary. If I can't detect that you like deviated from the protocol, I assume that this party was honest. And then this analysis goes through. Yes, more questions.
Can you get negligible soundness right away without parallel partition here?
In this setting, no. Wrong. In this setting, you can. Like you need to tweak the parameters of the MPC scheme in a clever way. Like you don't get away with like something as simple as we're going to see it. Vigero, for example, is a protocol that gets that by just running one multi-party computation. You can get negligible soundness. But the very simple MPC-in-the-head schemes don't get that. Like there you need repetition. Okay, one more thing, which is zero knowledge, and then the by now overpromised coffee. Okay. And zero knowledge is also like it's so dumb that we can just do that on one slide, right? So I mentioned that the MPC protocol has this privacy property, which says that if I open up to a threshold number of parties or an adversary corrupts these, then yeah, you don't learn anything but the inputs and the output. Like learning the outputs of the parties from the MPC in the head that's fine, right? Because all they learn is like one bit of information. Was the circuit evaluation correct? And since they got the secret sharing of the witness, you also like getting those secret shares doesn't give you anything about the original witness to begin with if you choose the threshold of the secret sharing accordingly, right? So just like now, instead of the prover being the one who corrupts the MPC-in-the-head parties, now you can assume it's the verifier corrupting these parties. But by the privacy guarantees of the MPC scheme, all is good. If you want to be a bit more formal here, right, you have to build a simulator for this. And you need to assume that your simulator simulates an adaptively secure MPC scheme, right? Because you're simulating all these views, giving them out to the adversary in a committed way, and only then the adversary is going to choose which parties to corrupt. So you're in an adaptive setting. And you need some so-called equivocable commitments, like standard commitments are not enough to make this go through. Yeah, I mean, that's what this says. If you are okay with honest verifier zero knowledge, which is fine in most of the cases, well, in that case, the simulator knows the choice of the verifier in advance. So all you say is like, I take my statically secure MPC protocol that I like and use this. Just like, interestingly, different flavors of MPC, like different security guarantees are needed depending on what kind of zero knowledge you actually want to prove here. Okay, that is clear so far. There's one more question.
Yeah, so for honest verifier zero knowledge, do you need equivocal commitments or you don't?
Then you don't need equivocal
don't need
commitments. Yes. Okay. I'll just quickly mention that it was introduced by Ishai et al. In, I think the other slide said 2007. It's like one of 2007, 2008. I think it was 7. And like the first implementation of this actually was only done in 2016 in a paper called ZK Boo. That was later optimized. Then also 2017 saw the first paper that actually does this kind of proof system, but where the community, like the size of your proof is sublinear in the size of the circuit that you're actually proving. And like maybe I can say one slide about this later. And then most of the MPC-in-the-head protocols that we had to date until, let's say, last year followed something introduced by John Katz and Vlad Kolesnikov and Xiao Wang in 2018, and they use MPC-in-the-head in the pre-processing model. And after the break, I'll tell you how that works. So go grab your coffee.